So on this question, we want to classify the given function as a polynomial, a rational, or a root, and then find the domain. And we want to write the domain in interval notation. So starting off, we want to identify which type of function we have. So we've got these three types of functions that we're working with, and we want to try to recognize which type we have. The rational and the root are more obvious than the polynomial. When you have a rational function, you're going to see a variable in the denominator, so something like 1 over x. When you have a root function, you're going to have something inside of a radical. So as I just said, for the rational functions, we're looking for something like 1 over x, a variable in the denominator. For the root function, we're looking for some variable underneath a radical. And then polynomial functions don't have any of these messy features. So you can see in this example, we do have variables that are in the denominator. And so we're going to classify this as a rational function. So we've got up here, rational functions are in fraction form. We're looking for the variable to be in the denominator. Now, once we know that we have a rational function, we do have restrictions. So the reason why we have restrictions is because rational functions are in fraction form. And the denominator is not allowed to be 0 because division by 0 is undefined. So because we're not allowed to have a 0 in the denominator, rational functions have this restriction. So we need to figure out for our function what those restrictions are. So we're going to create an equation where we take the expression in the denominator and set it equal to 0. So q of x is what we have in our denominator over here. So we're going to take the expression in the denominator, q of x, set it equal to 0 so that we can figure out what those restricted values are and what numbers need to be excluded from the domain. So we take this t cubed plus t squared minus 20t. This is the expression that we have in the denominator. And we're going to set it equal to 0 and solve. So this is called a polynomial equation. And we're going to solve this by factoring. We have a common factor of t in every term. So we start by factoring out the greatest common factor. And that leaves me with t squared plus t minus 20 equals 0. And then looking inside these parentheses, we want to factor some more. And this is a quadratic. We can factor it into two binomials. The numbers that go in the front here need to multiply to be t squared. So that's going to be t and t. The numbers in the back, they need to multiply to be this last number here, which is negative 20. So I'm going to try 5 and 4. Because 5 times 4 is 20. There are other choices. 2 times 10 is 20, and 1 times 20 is 20. But I'm choosing 5 times 4 so that I can get a 1 in the middle. So 5 and 4 are close to each other. I'm going to be able to get that 1. So we need a plus on the 5 and a minus on the 4. And if you're struggling with factoring, make sure you multiply that out and check. So if you multiply that out, you would get t squared minus 4t plus 5t minus 20. And when you add these two in the middle, that's going to give you that 1t that you're looking for. Okay, so once we have it completely factored, we're going to use the zero product property. And the zero product property says if you have a bunch of things multiplied equal to 0, that one of them must equal 0. So either t equals 0, or t plus 5 equals 0, or t minus 4 equals 0. And then you're going to solve. So we're going to subtract 5, and t equals negative 5. We're going to add 4, and t equals 4. So our restricted values are these values here, 0, negative 5, and 4. So I'm going to place these numbers on the number line so that I can figure out my domain in interval notation. So these numbers, these restricted numbers are negative 5, 0, and 4. We're going to mark them all with open circles because they need to be excluded from the domain. But all of the other numbers are going to be included in the domain. So then we need to represent each one of these intervals. So this interval starts at negative infinity and ends at negative 5. This interval starts at negative 5 and ends at 0. This interval starts at 0 and ends at 4. And this interval starts at 4 and ends at infinity. So we're going to be able to say that the domain of this rational function is negative infinity to negative 5, union with negative 5 to 0, union with 0 to 4, union with 4 to infinity. Notice I put parentheses on all of those numbers. They are not included in the domain. Parentheses means the number is not included. Classify the given function as a polynomial function, a rational function, a root function, and then find its domain. Write the domain in interval notation. The function that we want to classify is f of t equals the 9th root of 4t plus 1. So this one has a radical in it, and so it's not too hard to classify it as a root function. Roots and radicals are sometimes used interchangeably in math. So when you see a radical, specifically a variable underneath a radical, you have a root function. So this is going to be a root function, but then we want to figure out the domain of the root function. And we categorize the root functions by the index. So we take a look at the index, and the index is either even or odd. Now the index in this example is this 9 here. So that's the number that you see. I'm going to draw my 9 like this. That's the number that you see attached to the radical. And 9 is an odd number, so we know this is an odd root. Now that's important because we find the domain differently based on whether it's an even root or an odd root. The thing to remember here is that if we have an even root of a negative, we get I, which is imaginary or complex number. So in terms of real numbers, the radical is the even root is only defined for positive or 0. However, the odd root of a negative is defined as a real number. So an odd root will have no restrictions you can substitute positive numbers, negative numbers, 0, any real number into an odd root, and you will get an answer. So for our domain, what we're saying is on our real number line, we're allowed to use any of these numbers to plug into our variable. There's no restriction. So our domain will be the whole number line, negative infinity to infinity. So our domain of this odd root function is all real numbers, negative infinity to infinity. Classify the given function as a polynomial function, rational function, root function, and then find its domain. Write the domain in interval notation. So as we've said before, it's pretty quick to identify root functions. They will have a radical in them, a radical over a variable. So we're going to be able to say that this function is a root function. And then we need to get more detailed and focus on the index of that radical. The index is the number here on the radical, and we have an index of 6. So it's important to identify whether that index is even or odd, and this number is even. And the reason why it's important to do that is because we have restrictions on having an even index, but we don't have restrictions on an odd index. So for an even index, the square root of a positive number is going to be defined. The square root of 0 is going to be defined. However, the square root of a negative gives us an imaginary unit of I, and that is a complex number, and it is undefined in terms of real numbers. So we're only looking for real numbers, so we want to focus on these two cases. We only want what's underneath the radical to be positive or 0. So the way that we can figure out the domain of this when it's defined is to take what's underneath the radical and create the inequality greater than or equal to 0. Positive is greater than 0, and then 0 is equal to 0. So that's greater than or equal to 0, taking into consideration the two cases where it's defined. So then we're going to solve this inequality. I'm going to subtract 5. That gives negative x is greater than or equal to negative 5. We're going to divide by negative 1 to get x by itself. And we need to reverse the inequality symbol because we divided by a negative. So we get x is less than or equal to 5. I'm going to draw this on the number line. We're going to mark 5 with a filled in circle or a closed circle. And we want to shade less than 5. Less than is on the left. And we're going to write this interval in the interval notation. That's negative infinity for the lower bound and 5 for the upper bound. On the 5, because this is a closed circle, we're going to include it, so we're going to use a bracket. So on this one, we get a domain of negative infinity to 5 with 5 included. Determine whether the following equation defines y as a function of x. We have the equation x squared plus y equals 9. So this question is asking if this equation is y as a function of x. So I pulled up from our notes the definition of a function. And our definition of a function says, a function is a relation such that each element in the domain, for each element in the domain, there is exactly one corresponding element in the range. So the key part of this definition is this exactly one part. So if we kind of like summarize this definition, this is saying that every x has exactly one y. So we need to figure out whether this equation fits that definition. I also pulled in some bullet points from our notes that give us indicators of when something is not a function. So these are some indicators that can clue you in to a violation of that definition. So this is a tip to try solving for y. You want to write your equation as y equals, and that's going to help determine if you have a function. If you end up with a plus or minus, when you do that, that means that you have two y's for your x's, and that is not a function. When you have an even power on y, that's going to lead to the plus or minus, and once again, that is not a function. If you have absolute value around y, that's going to lead to the plus or minus when you solve for y, and so that is not a function. So those are some quick indicators. If you have an even power on y and absolute value on y, we have neither of those two things. So I'm leaning towards it being a function, but let's solve for y first. So if I solve for y, I would subtract x squared on both sides. That gives y equals 9 minus x squared. I don't have any plus or minus symbols, so this is looking like it is a function. Every x has one y. Now, if you want to feel a little bit more comfortable with it, you could try out a few x's. So what if I chose x equal to 0? Then y would equal 9 minus 0 squared. That's 9. We get 1 y value from that x. If I try another x equals 1. Y equals 9 minus 1 squared. That's 9 minus 1, which is 8. So we have an x that leads to 1 y. We can try one more. How about x equal 2? Y is equal to 9 minus 2 squared. 9 minus 4 is 5. So you can see that every x that I'm choosing is leading to 1 y, and that fits the definition of a function, and so we can say that this equation is a function of x. So yes, it is a function. In this question, we want to use the vertical line test to determine whether the graph represents a function. And we're given this graph over here. It's a little bit crowded with my words. But before we go over that, let's just think about what the definition of a function is. A function is a relation such that for each element in the domain, there's exactly one corresponding element in the range. So we want to know whether this graph here represents a function, and this is what a function is. It's a relation. A relation is any set of ordered pairs. And a graph is showing us a group of ordered pairs or a set of ordered pairs. So every single one of these ordered pairs that are on this line are included. We don't include this one with the open circle. We do include this one with the open circle, and then all of the other ordered pairs that are on the line make up this graph. So we do have a relation, but we want to make sure that this is a relation that for each element in the domain, there's exactly one corresponding element in the range. So this is the key word here, exactly one corresponding element in the range. And to do this, we have a test that we call the vertical line test that helps us decide that if every element in the domain, every x, corresponds with exactly one element in the range, one y. So when we do the vertical line test, what you do is you draw vertical lines everywhere on the graph. I'm going to especially pay attention to this kind of strange spot where the two lines kind of meet each other, and then all the other vertical lines along here. Now, when you draw these vertical lines, what you're paying attention to is how many intersection points you have. Let me use a different color. So this vertical line has one intersection point, and this one has one, and this one has one. And what that's telling us is that we have an element in the domain, whatever this value is, and it corresponds with only one y value. Because it has one intersection point, it's corresponding to one y. So as long as all of the vertical lines only have one intersection point, then we have a function. So let's pay attention to this long line, long vertical line I drew. This one has an open circle, which is not part of the graph, and this one has a closed circle, which is part of the graph. So that vertical line only has one intersection point, and we only have one intersection point on all of these vertical lines. And so that is telling us that we have a graph that does represent a function. So this is a function, yes. Thank you for checking out my videos. Have a great day.